Hey y'all, welcome back to A Slice of Physics. So we have been talking about magnetic fields and electric fields for a while now, and we have seen several relationships between the two as well as some critical differences. So for example, we saw that when you bring a charged rod near a compass, the compass does not deflect. So there is not a direct interaction between charges and magnetic fields. But on the other hand, we saw that any current has a magnetic field associated with it. And after all, a current is a bunch of charges moving in a direction. So the question we ask is, what are the conditions in which magnetic fields apply forces on charges? So in this video, we'll talk about when does an external magnetic field apply a force on a charge, and if it applies a force, how do we determine the direction of the force, which brings us to the second right-hand rule. First, let's talk about all the conditions in which an external magnetic field does not apply a force on a charge. So if I have an external magnetic field in this direction, so these arrows represent magnetic field lines, and I have a charge, let's say a positive charge that's just sitting here, or it could be a negative charge that's just sitting here. So this charge is stationary. In that condition, there is no force. Another example, if I have magnetic field, the same magnetic field pointing in the same direction, but now I have a charge, positive charge, that's moving parallel to the magnetic field in the same direction of the magnetic field, or negative charge moving parallel to the magnetic field. Again, you will not have a force from the magnetic field on the charge. All right, so when you have a moving charge that's moving along and parallel, this is not 11, the symbol stands for parallel to the magnetic field, there is no force. And the third condition in which there is no force is when it is moving parallel but opposite, directly opposite to the magnetic field. So in this case, if I have a positive charge moving directly opposite the magnetic field or a negative charge that's moving directly opposite the magnetic field, there is no force. All right, those are all the conditions in which there is no force from the external magnetic field on a charge. But what if the charge is moving in this direction? So it's not moving parallel to the magnetic field, it's not moving opposite the magnetic field, but it's moving at some angle. Let's take a closer look at that example. So if I have an external magnetic field, by the way, a magnetic field is not from the charge, it's from something else. It could be from a magnet, it could be from a current, but we don't care where it's from, but there is an external magnetic field. And let's say there's a positive charge that's moving in this direction. And this is the velocity vector of the charge. So right away, we can use our knowledge of vectors and break this velocity vector of the charge into two components. So I can break it into a v parallel. Again, this is not 11. The symbol that looks like 11 is parallel. And then v perpendicular. So what we mean by this is that there is a component of the velocity that's parallel to the external magnetic field B. And then there is a component of the velocity that's perpendicular to the external magnetic field B. The one that matters for force from the magnetic field on the charge is just the perpendicular component, because we've just discussed that any charge that's moving parallel to the magnetic field, whether it's in the direction of the magnetic field or directly opposite it, does not experience any force. So that component of the velocity does not experience a force from the magnetic field. It's just the perpendicular component that does. So if I take a couple of more examples, if I take a velocity vector that's exactly the same length as before, but at a shallower angle, now you can see that most of this velocity vector is parallel to the magnetic field and the perpendicular component is pretty small. So in this case, the force will be small. In our first example that we took here, the force will be larger. And if the charge is moving in this direction, then there is no parallel component. So the entire velocity vector is perpendicular to the magnetic field. So in that case, the force will be max. So the force will be maximum when v, which is the velocity vector of the charge, is perpendicular to b, the external magnetic field. This is the symbol for perpendicular. All right, now that we have talked about when there is a force and what it depends on, it only depends on the perpendicular component of the velocity. Let's talk about how we determine the direction of this force. So let's take the example once again that the external magnetic field points from left to right. It's fairly uniform in the region of space that we are interested in. So here's my B, and then let's say the positive charge is moving in the upward direction like so. So to determine the direction of the force from the external magnetic field on this charge, we use the second right-hand rule. Your textbook has a way of describing the second right-hand rule when they use three fingers. They use the thumb, the index finger, and the middle finger. That gets a little hard for me to illustrate in these videos on a two-dimensional screen. Plus, another technique is easier for you guys to use where your chances of making mistakes are lesser. So I prefer a different notation that I'm going to go over in this video and in class, although I will talk a little bit about how the textbook does in class as well. And then the added advantage of this method is that it is also politically correct. When you have three fingers in your hand that you're holding out and one of them is a middle finger, sometimes it ends up being held in an awkward position. So the way this works is when you hold your right hand flat with your thumb perpendicular to the rest of the fingers, as if you're approaching somebody for a very formal handshake. So I'm going to draw the palm as if you're looking straight at it. So let's say here's your thumb, and here are your fingers, and here's the rest of your palm, and here's your hand. All right. Not a great picture, but I'm not a good artist, sorry. So when you hold it like this, the first thing you want to make sure is that you are using your right hand. Even if you're left-handed, please make sure that you're using your right hand. Second, the thumb points in the direction of motion of the charge. Third, all of these fingers point in the direction of the external magnetic field. And when you do that, your palm faces in the direction of force from the external magnetic field on the charge that's moving. So this charge here is Q. All right, those are the rules of the second right-hand rule. So in this example, the force will be out of the screen because that's how your palm is facing. So if I were to show the force as a vector, I would use these notations. Remember, we said for vectors, a dot means you're coming out of the screen. Okay, there's one other very important point to this second right-hand rule. This only works for a positive charge. So if the charge is negative, then you have to reverse your answer. So you still use the second right-hand rule in the way that we described here, thumb pointing in the direction of the motion of the charge, fingers pointing in the magnetic field direction, and then the palm will give you the direction of the force. But then if it's a negative charge, you reverse that direction. So the force is out of the screen on a positive charge. And if it's a negative charge that's moving, I have to reverse it. So I will have the force going into the page if the charge is negative, force on negative charge. All right, let's apply this to our example. So in this case, I have the magnetic field going to the right, and I have the charge moving up. So I still use my right hand, but I have to orient my thumb pointing in the direction of V. I've got to orient my fingers pointing in the direction of the external magnetic field. So I'll be holding my palm like this. And when I do this, you realize that I am actually seeing the back side of my palm, right? So here are my knuckles, and in order for me to hold my right hand like this, I encourage you to try it. You're not going to be seeing the inside of your palm, you're going to be seeing the back side of your palm. So you will not have these lines that I showed here that our palm has, they are on the other side. So here I have nothing. I might have some veins running this way and stuff. So when I hold it like this, the force is going into the page. So in this example, with the magnetic field, external magnetic field pointing to the right and a positive charge going from bottom to top, the direction of the force will be into the page. And so I'll show that as x's. So one property that you see here is that the external force from a magnetic field on a moving charge is perpendicular to both the direction in which the charge is moving as well as the external magnetic field. It'll always be that. So it's in a different plane than those two things lie, which is why we need all these symbols to describe things that are moving in the plane of the screen or the page and things that are moving perpendicular to it, into or out of. So the force is always perpendicular to the B and perpendicular to V. So in this case, an arrow that's going directly into the page does satisfy those two conditions. So we covered a few things. We are talking about magnetic force on a charge. And the first thing we did is realize that an external magnetic field does not apply a force on charges in certain conditions. So those conditions are when the charge is stationary, or it's moving along the magnetic field, or it's moving directly opposite the magnetic field. And then when it is moving in a direction that is not one of those when there's no forces applied, then we realize that the direction of the force is perpendicular to both the direction of motion of the charge and of the external magnetic field. It's maximum when the charge is moving perpendicular to the magnetic field because we only care about the perpendicular component of the velocity. And then the second right-hand rule helps us determine the direction. So to recap, we hold our hand flat with the thumb perpendicular to the fingers as if you're approaching somebody for a formal handshake. Make sure you're using your right hand, even if you're left-handed. And then you move your hand and rotate it so that your thumb points in the direction of the motion of the charge or its perpendicular component, since that's all we care about. The fingers point in the direction of the external magnetic field B, and then the palm will be facing in the direction of the force from B on the charge Q. And then one very important thing is that the second right-hand rule, as described so far, only works for a positive charge. And so if it's a negative charge, then you reverse whatever answer you got from using the second right-hand rule. Thank you.